Hello everybody, welcome back to my calculus class. We will talk about Taylor series and Maclaurin series. So enjoy it. Today we are going to talking about the Taylor series and Maclaurin series. We can use the polynomial function px to approximate a function fx by p of x equal to c0 plus c1 x minus a, c2 x minus a to the power 2, and c3 x minus a to the power 3 until the end of the series cn x minus a to the power of n, where c0, c1, c2, c3 to the cn are the coefficients of x minus a to the power of 0, x minus a to the power of 1, x minus a to the power of 2, until x minus a to the power of n. We want to find out the values of C0, C1, C2 to Cn. We differentiate the functions by the first order, second orders until the nth order. In step 1, we assume that fx equal to C0 plus C1 x minus a until Cn x minus a to the power of n. We let x equal to a. We have fa equal to C0 plus 0 plus 0's all the term to 0. Therefore, we get C0 is equal to fa. In step 2, we differentiation the function once. We have the first differentiation of fx is equal to 0 plus c1 plus 2c2 x minus a plus 3c3 x minus a to the power of 2 plus 4c4 x minus a to the power of 4 until n cn x minus a to the power of n minus 1. And then we let x equal to a again. We have f dash a is equal to c1 plus 0 and all 0. Therefore, c1 is equal to f dash of a. In the first step, we differentiate it again. So we got the second derivative of fx is equal to 0 plus 2c2 plus 2 times 3 x minus a plus 3 times 4 x minus a to the power of 2 until n minus 1 times n times x minus a to the power of n minus 2. And again, we let x equal to a. The second derivative of fa is equal to 2c2. So c2 is equal to half of the second derivative of fa. We do this one more step, step 4. We have the third derivative of fx is equal to 2 times 3c3 plus 2 times 3 times 4c4 x minus a until n minus 2 times n minus 1 times n cn x minus a to the n minus 3. And then we let x equal a again. We got the third derivative of fa is equal to 2 times 3c3 plus 0. So we know that c3 is equal to 1 over 3 factorial, the third derivative of fa. Therefore, we have fx can be approximated by px equal to fa plus 1 over 1 factorial, the first derivative of fa, x minus a. And 1 over 2 factorial, the second derivative of fa, x minus a to the square, and the 1 over 3 factorials, the third derivative of fa, x minus a to the cube, until 1 over n factorial, the n derivative of a, x minus a to the power n. If a is not equal to 0 and we have a limit terms of this polynomial, we call this polynomial the Taylor polynomial. And if we count to the n terms where n tend to infinity, we call this a Taylor series. And if a equal to 0, we can approximate the fx by px, and it is equal to f0 plus 1 over 1 factorial, the first derivative of f0 x, plus 1 over 2 factorial, the second derivative of f0 x squared, plus 1 over 3 factorial, the third derivative of f0 x cubed, until the terms 1 over n factorial, the n derivative of f0 x to the power n. And if we have a limited term, we call it a Maclaurin polynomial. And if the terms is extend to the n terms where n tend to infinity, we call it a Maclaurin series. And this is how we define the Taylor series, Taylor polynomial, Maclaurin series, and Maclaurin polynomial. We will have an examples of Taylor series to estimate a function. Now we have an example. We try to find the Taylor series of the function, then also find the radius of convergence of this series as a equal to 1. And the function itself is log x. And we estimate the function, and at the point x equal to a equal to 1, we try to find the Taylor series of it and the radius of convergence of it. I like to do is to write out a tables of n term and also the n derivative of this function. Also the n derivative of this function at the point a, and also the n factorial as well. Let us do 4 terms of it. N equal to 0, 1, 2, 3, and 4. The function itself is log x. The first derivative, 1 over x. X to the power minus 1. The second derivative, minus x to the power minus 2. The third derivative, plus 2x to the minus 3. The fourth derivative, minus 6x to the minus 4. And if we put a equal to 1 into this derivative function, we have log 1, 1, minus 1, plus 2, and minus 6. N factorials, 1, 1, 2, 6, and 24. And the Taylor polynomial to the fourth derivative is fa plus 1 over 1 factorial. First derivative of fa, x minus a, plus 1 over 2 factorials. The second derivative of fa, x minus a squared, plus 1 over 3 factorials. The third derivative of fa, x minus a to the power of 3, and plus 1 over 4 factorials. The fourth derivative of fa, x minus a to the power 4. When a is equal to 1, we substitute the above table into this series. We have log 1 plus 1 over 1 factorial times 1 times x minus 1 plus 1 over 2 factorials times minus 1 x minus 1 to the square plus 1 over 3 factorials times 2 times x minus 1 to the power of 3 plus 1 over 4 factorials minus 6 times x minus 1 to the power of 4. In here, I want to take out the general terms of this series, and I know that is n equals 0 in this term here, n equal 1, n equal 2, n equal 3, and n equal 4. So I will write this Taylor series by, I take out the first term when n equal to 0, from the n equal to 1 to infinitive, I get the n terms of this here. So in here, I got the 1 over n factorials. So this one should be n factorial at the bottom. And at the top, I have 1 here, minus 1 here, 2, and minus 6. So this one should be n minus 1 factorial. So when e equal to 1, 1 minus 1 factorials is 1. N equal to 2, 2 minus 1 factorials is 1 as well. I just ignore the negative side. And if this is n equal to 3, 3 minus 1 factorial is 2 factorial is 2 here. So I get this value here. And for the x minus 1 to the powers of n, so this one is the x minus 1 to the power of n. So this should be the n terms of this Taylor series. So I simplified the n term of this Taylor series to here. Now I want to find out the radius of convergence. And also for the alternative negative side from the n equal 1, n equal 2, 3, and 4. So I multiply by minus 1 to the power of n plus 1. Now we are going to use the ratio test to find out the radius of convergence of this Taylor series. After simplifying, we have log 1 plus the summations of n equal 1 to infinitive minus 1 to the power of n plus 1, n minus 1 factorial, x minus 1 to the power of n, and over the n factorials. By the ratio test, you got the limit else if the n is tend to infinitive, the absolute value of a plus 1 term over the a terms should be less than 1, and this one should be convergence. Now we are trying to find the limits when n tend to infinitive, the a n plus 1 term over a term is less than 1. We just put the n plus 1 into the n here. So we have minus 1, n plus 2, n to the factorial and x minus 1 n plus 1 over the n factorial should be n plus 1 factorial and divided by the a n term, so we have to multiply by its reciprocal. So we multiply by n to the factorials over minus 1 to the n plus 1 term, and this is n minus 1 to the factorials and x minus 1 to the power of n. We take the absolute value of the limit. We simplify minus 1n plus 2 over minus 1n plus 1. We have minus 1 to the power of 1 at the top. And n factorials, n minus 1 factorials, we got n left here. So this one cancel as well. N factorials, n plus 1 factorial at the bottom, so we get n plus 1 at the bottom. These two cancel. X minus 1 n plus 1, x minus 1 n, so we have x minus 1 at the top, the limit. And we take out all the terms where there is no n in here, so we only get is equal to the absolute values of minus 1, x minus 1. Take out this, multiply by the limit n tend to infinity, absolute values of n over n plus 1. And then these two values, minus 1, x minus 1, the absolute values is equal to x minus 1 to the absolute value. And then the limit n tend to infinity, we divide the numerator and the denominator by n. We get n over n plus 1 over n. Finally, we have x minus 1 absolute value multiplied by the limit n tend to infinity, 1 over 1 plus 1 over n. When n tend to infinity, this one will go out because this one will return to 0, so we have 1 here. So we left out is the absolute values of x minus 1 is the limit of this series. And if we want to make it convergent, we have to let limit of this series is less than 1. Then this should be convergent. And if this is less than 1, we know that the radius of convergence is equal to 1 here. Because we know that is minus 1 is less than x minus 1 and less than 1. So we add 1 into this term here. We have 0 is less than x is less than 2. So we know that the x is less than 2 is greater than 0. So this should be from 0 to 2, and at the midterm x is equal to 1. So the radius of convergence should be 1 here. So we got the radius of convergence of this Taylor series is equal to 1. This is how we solve the Taylor series. So in conclusion, the function log x, and we take the point a equal to 1. The Taylor series should be this one here. And the radius of convergence should be 1 here. It's all for this lesson, and see you next time. Good luck and do good math.